Good evening, all. Am I audible to all?
Yes, ma'am.
Okay. So let's start week 8 live session for characterization of construction materials NPTEL course. Sorry, I'm not feeling so well, so might be my voice might not be properly audible. So please stop me by any point of time if my voice is not audible. Okay. So this week we'll be seeing content from scanning electron microscopy, and I am Nilakanmani. I am one of the PMR of NPTEL TAs for this course, Characterization of Construction Materials. Uh, Now let's get into the course content. Let's see the first question for this week. This question is not launched in polls, so please go through the question here and type your answer in the chat box. Okay. So the question one is, why is vacuum necessary in scanning electron microscopy column? SEM column. Why is vacuum necessary? Okay. Let me start the timer for a minute now. This particular question has more than one right answer. Okay. So here are the options. Gases may interfere with the electrons. That is first one. Second one is gases can cause electrons in the beam to ionize. Option C is transmission of electron beam through optic column will be hindered by the presence of other molecules. And option D is gas interaction with the electron beam would lower the contrast and obscure detail in the image. Which could be the following reasons and to say why vacuum is necessary in SEM column. Time is up. Let's see the class response. Option A. Okay. Let's see the solution. So most of you have felt option A is right. Let's see what's the correct answer. See, when it comes to vacuum, gases may interfere with the electrons. So if there is some gases inside the column, it may interfere with the electron, and the gases could react with the electron, and the electrons will uh, cause electrons in the beam to ionize. That is also possible, and the transmission of the beam also will be hindered, and overall it will affect the image also. So in that case, contrast will be affected, it will cause obscure detail in the image. So in that case, all the given options are right, not only A. Okay, so what kind of gases interfere with electrons, and after interfering, what can happen is the other three options given here. So all the options given here are correct. Okay, so now let's move to the next question. What is the function of electromagnetic lens in SEM? So we know that SEM column is there and sample holder is there in SEM equipment. So in that, electromagnetic lens is also there. What is the function of electromagnetic lens is the question. Okay, let me start the timer for a minute now. If you know the schematic diagram of SEM, it should be easy for you. And it is discussed in first few slides of the lecture in SEM. Time is up. This question is launched in polls. I didn't mention it well before, but I have given you answer in polls. Okay, let's see the class response. Okay, focus the electron beam. Nice. Let me end the poll. I can understand that you have to type something, right answers in the chat box for MSQs, but for MCQ, I request everyone to give your answer in the polls because it's very easy that you can pick any one of the option and none of you will know who has given the right answer or wrong answer. Okay, so better than coming and being in the class and not answering, try to give some answers so that you can have some understanding. Let's see the pictorial image of the SEM column here. So first we could see some electron gun. After that there is some anode plate. It comes through here. And there is some magnetic lens and scanning coils and all. So here the magnetic lens is there, right? Electromagnetic lenses, not only magnetic lens, electromagnetic lenses. Focus a beam of electron that are accelerated through a large potential difference. So electron is generated from this electron gun. It passes through the anode plate. Then it goes through the magnetic lens, electromagnetic lenses. Okay, so this helps to focus the electron beam to pass down through the coils, lenses, magnetic lenses. Okay, so now let's move to the correct answer is option B. Next question also please give your answer in polls. Okay, this question is launched in polls. To the people who have joined new, to the bottom right corner of your screen, there is some square, triangle, circle, things and all will be together. Square, triangle, circle will be together. If you click that, you will find activities. If you click that, you will find 4 options. Out of that, you have to click polls and go and give your answers. If you're using a mobile phone, there will be 3 dot. If you click that, near the screen, so in that if you click that you'll reach activities, then you should go to polls and give your answers. Question 3 is already launched in polls. The question is positive potential. It's a true or false question. Positive potential is applied to the Venel cap to increase the potential difference between Venel cap and anode plate to accelerate the electron beam. So in the previous slide, we have shown you that electron gun is there. Electron beam is generated from the electron gun. It passes through the anode plate. Actually, surrounding this electron gun, there is a Venel cap that is not shown in this image, but there is a Venel cap also. So here the statement is positive potential is applied to the Venel cap to increase the potential difference between Venel cap and the anode plate to accelerate the electron beam. Okay. So let me start the timer for a minute now. If you find the statement is correct, please give your answers, or if you feel it wrong, then you can choose false. Time is up. Let's see the class response. Okay. There is some mixed response here. Okay, let's see the solution. Let me end the poll. Here, if you see, this is the filament, so tungsten filament or any other filament. So from that electrons will be generated. Okay, so this is the anode plate and this is the Venel cap. Venel cap is always has negative potential, so negative potential is applied to the Venel cap, and then the anode plate has a positive potential. We also know that electrons are negatively charged. In that case, since both are negatively charged, it will not attract it to the sides, it will just directly pass through this, uh, pass to the outlet to the Venel cap. And then since anode plate is positively charged, we know that opposite charges attract, so the the velocity of the electron beams which pass through this Venel cap and reaching this gap and anode plate also will be accelerated further because of the potential difference between the Venel cap and the anode plate. Okay, so in that case the correct answer is false, because here you have told that positive potential is applied to the Venel cap. That is wrong. Negative potential is applied. Okay. So now let's move to question number 4. You have to give the answer for question 4 in chat box. This is not launched in polls. It's a match the following question. Sorry. So in this case, we have there are 3 different modes that in which scanning electron microscopy is done: secondary electron, backscatter electron, X-rays. Using EDX, we'll be able to use the X-rays also. So we have to match the output from scanning electron microscopy to its application here. What could be read from, or what could be analyzed, or what could be observed from the secondary electron or backscatter electron or X-rays generated from the electron beam, interaction of electron beam with the sample. Okay, once the primary electron beam interacts with the sample, there can be 3 different types of things that which we can. Okay, sorry, rather than talking, I'll draw it so that it will be, assume that it's a SEM column, it's coming, the electron beam is coming to the SEM column, and here is the sample. Okay, so in that case, if it interacts here, different observations can be different uh, observations can be made here. Outputs can be here. So one is secondary electron. In the case, it has low energy compared to the backscatter electron, so it goes like this. Here we have some secondary electron collectors. Okay, and when it comes to backscatter electron surrounding the to the end of the SEM column itself, there will be an annular ring set around the SEM column by the end, which the backscatter electron collector will be there. So here that also will be collected here, and along with this there will be an EDX analyzer, energy dispersive X-ray spectroscopy, that will also be kept separate, with which the interaction also gives rise to X-rays, so that will be absorbed by the EDX analyzer. Okay, so in that case, with secondary electron what will be measured, and with backscatter electron what can be observed, and X-rays what we can observe. Already I've taken more time. Let me start the timer for a minute. Please match the appropriate answers. Time is up. Okay. A3, B2, C1. Let's see what's the right answer. So the correct answer is A3 is right, B is actually not 2, 1 and C is 2. So let me explain this. So, and when it comes to secondary electron, we'll be able to understand the morphological information because these are low energy electrons rising after the interaction. So mostly the surface, since the electrons of low energy comes out, mostly it comes from the surface. So we'll be able to understand the morphological information from that. And when it comes to backscattered electron, we'll be able to understand the compositional contrast because when it comes to backscattered electron, these are high energy electron beams arising after an collision from the nucleus. Okay, so in that case, it directly bombards and hits the annular ring around the SEM column at the end, which is the backscatter electron detector. Okay, so in that case, we'll be able to understand the compositional contrast. So if say if you take unhydrated cement phase, it will be unhydrated cement will be more denser, and if you see if you compare Portlandite and CSH, in both the cases Portlandite will be even more denser compared to CSH. So in that cases it will appear bright compared to CSH. Portland will be even more bright, so that the different phases will appear in different contrast. Okay, so in that cases compositional contrast is the major thing that we observe from the backscattered electron. When it comes to X-rays, we measure the elemental composition. In that case, we'll be able to understand the phases present. See, if you want to understand the calcium to silica ratio, or if you want to differentiate CSH and cash. Okay, let me write it here. If you want to understand the difference between CSH and cash. Anyway, here there should be hyphen in between. Sorry, I missed it. Okay, so in that case, if you do some spot analysis in a sample, if you get only calcium to if you are doing some 100 spots here, okay, like this, you are doing some 100 spots, taking a small zone and doing some spot analysis like this, and if you get only the presence of calcium and silica, then you can say what is the phases present over there. It can be unhydrated cement also, but if you know that there is a difference in contrast and this appears to be not that bright, then we can say it's CSH. What if it has calcium, silica and alumina also? In that case, that could be related to CaSH. Okay. So this kind of things can be observed only from X-ray dispersive spectroscopy, EDS, energy dispersive X-ray spectroscopy. Okay, now I hope you guys got it right. Now let's move to the next question. Next question is not launched in polls. You have to type the answer in chat box. Okay, identify the true statements regarding SIMS. scanning electron microscopy, you have to find the correct statements. There are 4 statements here. Please go through all the statements and please give the right answer. First thing is specimens must not have any moisture content. Option B is the electron beam must pass through an evacuated chamber. Third is SEM can be used to observe the internal structure of the sample and not the surfaces. Option D is SEM can provide a three-dimensional image of the microstructural features. Okay, let me start the timer for a minute. Please type the answer in the chat box. Time is up. Let's see the class response. ABD. Okay, someone felt AD and some felt ABD. Let's see what is the right answer. So the correct answer is A, B and D. Not only AD, it's ABD. So we all know that there should not be any moisture content because in the high vacuum if there is some moisture in the sample it might block the SEM and it will totally affect the equipment. So it should not contain any moisture content, and the electrons beam must pass through an evacuated chamber only. That should be there, and we have a high vacuum system to control that also. And then SEM can provide three-dimensional image of the microstructure feature. Yeah, it can provide. When it comes to secondary electron imaging, you can see the fractured surface properly, and crystals like yttringite, portlandite and all can be properly viewed in secondary electron imaging. Okay, so and here in option C, SEM can be used to observe the internal structure of the sample and not the surface is totally false because we are seeing only the surface and not the internal structure of the sample. And I didn't properly explain this thing I felt during discussing the fifth question. So here most of you would have thought that elemental composition is what we get it from X-ray EDX, right? So in that case here the thing is not elemental composition, compositional contrast. In any case we cannot get composition contrast from X-ray dispersive spectroscopy. You will get the where you'll get to know the presence of certain elements using EDX. So in that case, we'll get to know about the phases here. And if they're given only elemental composition, then you can say it's X-rays. Okay, but when it comes to compositional contrast, it's backscatter electron. Okay. So now let's move to the next question. Question number 6. It's a true or false question. A Faraday cage is required to facilitate the larger collection of backscattered electrons. So I've told you that there are different uh, uh, collectors, like secondary electrons will be collected separately and backscatter electron will be collected separately, and we have separate thing to collect the X-rays generated during the interaction, right? So in this case, they are asking a Faraday cage is required to facilitate the larger collection of backscatter electron. Say whether it's true or false. I'm starting the timer now. Time is up. Let's see the class response. Okay, Faraday cage is required to facilitate a larger collection of backscatter electrons. Okay, let's see what is the right answer. Most of you have selected it's true. So here, secondary electrons are low energy electrons as discussed. So they are collected by placing a positive voltage on front of the detector called Faraday cage. So Faraday cage is used for secondary electron or not backscattered electron. Okay, and the type of detector is used is called as scintillator and then or photomultiplier tube. Okay, so in most of the cases the collecting thing will be of positive voltage because electrons are negatively charged, so we need positive voltage to collect the secondary electrons arised from the interaction. Okay, so now the correct answer is false. Now let's move to next question. So question 7 is secondary electron arises due to either inelastic collision or elastic collision between primary electron, that is electron beam, and the loosely bound outer shell electrons. Backscattered electron arises due to inelastic collision or elastic collision. You have to find what is right, and between the incoming electron and the nucleus of the target atom. So here in all the cases in secondary electron, it arises due to the collision between electron beam and the loosely bound outer shell electron that comes out. Okay, this electron beam comes and knocks out the outer shell electron. That is where the secondary electron arises. And then when it comes to backscatter electron, the backscatter in backscatter electron, what happens is the primary electron goes and hits the nucleus of the target atom and bombards and comes back directly, and it is detected by the backscatter electron detector, right? So here which of the following is elastic and inelastic, you have to state. Okay, let me start the timer now. This question is launched in polls. Please give your answer in polls. Let's see the class response. Okay, most of you have given the right answer. Nice. Let's see the solution. So the correct answer is nothing but inelastic collision, elastic collision. So when it comes to secondary electrons, the collision is not elastic collision, it's inelastic collision. And when it comes to backscatter electron, it directly hits the nucleus and comes back directly. It's just reflection. So the elastic collision happens. Okay. So now let's move to the next question. This question is not launched in polls. So you have to type the answer in the chat box. So the question is, the interaction volume of the electron and the sample increases with. How we can increase the interaction volume? We know that the electron beam comes and interacts with the sample. How we can increase the interaction volume? Okay, that is the question. First option is increase in the atomic number of the elements present in the sample. Okay, we have to increase atomic number of the elements present in the sample. Then option B is increase in the accelerating voltage. C is increase in the angle of incidence. And D is decrease in angle of incidence. So you have to pick the right options. This has more than one right answer. That's why we choose this multiple select question. Let me start the timer for a minute now. Time is up. Let's see the class response. Okay, B and D. Fine. Let's see the correct answer now. So accelerating voltage, if it's higher, there will be more penetration, higher volume. So in that case, increase in accelerating voltage is the correct answer. And angle of incidence for the electron beam greater. So there should be increase in the angle of incidence. Assume that uh, the sample is here. Okay. And if the angle of incidence is an acute angle like this, then the amount of sample interaction will be very very less. Okay, so but if it directly comes and hits perpendicular, so as much as perpendicular it has the interaction volume will be higher. So in that case, the angle of increase in angle of incidence and increase in accelerating voltage helps in better interaction volume of the electron and the sample. Okay. Okay, now so now the correct answer is option B and C. Now let's move to the next question. This question is launched in polls. Please give your answer in polls. Which of the following microscope techniques gives the maximum depth of field? I know that you guys know what is depth of field. So, which is the so if you focus at a particular point, assume that if you particularly assume it's a mobile camera. So if you are planning to focus at particular point here, okay, so here the focus will be more appropriate, but exactly here when we move about a centimeter here, the focus will not be completely lost to a certain distance on both the sides of the exact focus point. If you're here with a camera or a mobile phone, if you try to capture this, okay, the depth of focus will be good here. The focus will be good here, but to a certain depth on either side, there will be a good amount of focus will be there. So in that case, that is the depth of focus. Okay. And if you have to think in terms of SEM, you can think in that way. Okay. uh, which of the following spectroscopy or microscopy techniques will microscopy techniques will have maximum depth of focus? Option A is optical microscope, B is stereo microscope, C is scanning electron microscope, D is transmission electron microscope. Okay, let me start the timer now for a minute, and please give your answer in polls. Time is up. See the okay. Someone of you have felt transmission electron microscope. Okay, fine. Let me end the poll here and go to the solution. So the correct answer is scanning electron microscope. Transmission electron microscope, actually it has a very when you compare scanning electron microscope, transmission electron microscope has a lower depth of field, because when you take higher depth of field, when you increase the depth of field, the resolution we expect can't be achieved. Okay, so in that case, scanning electron microscopy, like when it comes to resolution, transmission electron microscope has better resolution than scanning electron microscope, because it just passes through the material. We prepare thin samples out of the sample of interest, then we pass through the electron beams through the sample, then it goes through the material. So after absorbance, whatever is transmitted further, we study that for understanding the material, understanding the sample. Okay, when it comes to transmission electron microscope, the depth of field is very less compared to scanning electron microscope, and out of all these features, scanning electron microscope has maximum depth of field. Okay, so now, and in this case also, if the depth of field is higher and higher, obviously the resolution we require might not be achieved. So we have to always play with the terms and get better resolution as well as good depth of field also. Now let's move to the last question for this week. Question number 10. This is also launched in polls. Which of the following mode is ideal for EDX analysis? I hope you guys know what is EDX analysis now. We will be able to understand the elemental composition present in the sample. Okay, so we have two modes, major two modes in SEM, scanning electron microscope. We call them as secondary electron mode or backscattered electron mode, right? Uh, in that case, we have detectors separately for scanning electron, and then backscatter electron detector also will be there. Okay, which of the following mode is ideal for EDX analysis? Okay, you have to find the right answer. Either it's scanning electron mode or backscatter electron mode, or both A and B, or none of the above. Okay, let me start the timer now. If you know the answer, please give it in polls, and if you know why, you can type it in the chat box. Why a particular mode is ideal for EDX analysis, you can type. Time is up. Let's see the class response. Okay, secondary electron mode. Fine. I don't know why you felt secondary electron mode, but let's see the response. Let's see the correct solution now. So, when it comes to EDX analysis, uh, let's see secondary electron and backside electron mode. Then you'll get to know easily. Uh, See, BSC mode is more ideal. BSC mode is more ideal for EDX analysis. Secondary electron mode should be carefully adopted because the specimen must be flat, stable, homogeneous, and void free. So in that case, see, we know that how we have to prepare the sample for backscattered electron mode, right? In last class, we have taught about epoxy impregnation, how we need to polish them, and after that, since concrete samples are non-conductive, we have to coat them with gold or carbon coating so that charging will be avoided, right? In that case, I'm just trying to recall the stuffs that we discussed in the last class about the specimen preparation for SEM analysis, right? So in that case, secondary electron mode, if you see, the samples are not flat at all. Okay, we are trying to take a fracture surface. Okay, we're trying to take a fractured surface and then try to understand the why fracture happened here, or to see the presence of heterogeneous crystals kind of things. We just do it using secondary electron mode. When it comes to backscatter electron mode, the sample should be flat, right? It should be flat so that when the electron beams hits, it just directly comes back and is detected by the backscattered electron detector. Okay, so in that case, if you see, there is some crust and tuff here, right? Crust is here and tuff is here. So this undulation is always there. So at a particular point, if you take uh, uh, let's assume that a secondary electron detector is here. So if the electron beam comes and hits here, since this is here, at certain cases it might not be able to reach the detector. Okay, and here, even if it hits, obviously here it can't come back, right? So in that case, secondary electron mode is not ideal for EDX analysis since the surface is not flat. BSC mode, why it's ideal? Because of the stable, flat, homogeneous, and void free. Because we impregnate them with epoxy, the voids are filled with epoxy now. So we know that epoxy is not that dense compared to the concrete specimens. Obviously, it will appear dark only in backscatter electron analysis also. I think in the next lecture is about image analysis, how we analyze the same images. In that case, you will be able to know how pores will appear in backscatter electron image, how unhydrated faces will appear, how hydrated faces will appear, and all you'll get to see in the image analysis. And I hope some of the lectures you guys would have, if you see the second part of the lecture, like If you take SEM and if you see the second part of the lecture, you will get to see more SEM images, and sir would have described which one is hydrated phase and which one is not hydrated, and how we can differentiate based on the contrast and all. So in that case, you'll be get to know voids or pores will appear dark in the SEM analysis if you take the image. I hope you guys got it right now. And this is the last question for this week. Do you guys have, let me stop presenting. Do you guys have any more query? Okay. Okay, fine. Let me end up the class here. Thank you. Thank you for being so patient.